Bismillah ar-Rahman ar-Rahim. Dear students, it's now time to apply whatever we have learned into one particular algorithm, this process scheduling algorithm that's called as the multi-level feedback queue. So this algorithm has everything in it, okay? It works twofold. It minimizes or optimizes the turnaround time, as well as it minimizes the response time as well. Okay, so what we have learned until now was firstly the first come first serve. That was kind of very simple. It has a comma effect problem. We discussed that, and to minimize that, we say SJF, shortest job first, which was non-preemptive, and then we say okay, preemptive version SRTN, which is much better. But the problem was how to say particular job is, the short or it's big. Okay, so you don't have an a priori knowledge and you want to increase you minimize the turnaround time and all, but you can't do it in a SJF. Okay, so you say you don't know how long a process is, so saying this is short or not, that doesn't work. Okay, so we tried round robin. Round robin was working wonderfully well. It was really nice. Because it makes every process happy. Okay, so response time actually was wonderfully well in round robin, but the problem with the round robin was it was terrible in the turnaround time. So now whatever we have learned, we can apply all those things into a particular algorithm. And what we want that we don't know, actually we don't know how this is a short process or not. If we know a priori that this is a short process, then it's not a problem. SJF or SRTF is a wonderful algorithm, but we don't know. That's the problem. We don't know exactly that this is a short job. So we can know it, but when it runs. So that's why we have multi-level feedback queue. So we don't have one queue ready queue now. We may have many queues, and there's a feedback mechanism where we can understand one execution about this job. And accordingly, our scheduler will take decision that should it be having a high priority or low priority or whatever it is. Okay, so let's try to learn this algorithm now inside out. Okay, so stay tuned.
Okay, before we talk about the multi-level feedback queues, we need to first talk about multi-level queue. Okay, this multi-level queue scheduling actually lead us to the multi-level feedback queues. Okay, this is we saw that the processes have different actually needs. Okay, now some are input output based processes, some are CPU intensive, I can say, processes, some are having input output intensive processes. So some processes are very high priority, like we have a system processes, and we can have different kind of processes. Okay, and we can therefore, if we wanna, we have one ready queue. Until now, we just had a one ready queue, and we put everything into it, all processes into it, and we see that some process is very interactive, which needs basically, if some process is interactive, maybe it's also the IO based. It needs some kind of interaction one way or the other. So in these processes which are more interactive, need to have more response time. I mean, a quick response time. Okay, but there are some processes which can run for a long time and they don't need any intervention. So you can make a batch out of it. So we can call them as a batch processes. Okay. So different processes, okay, have different scheduling needs. Is it? So it is this idea that if we can easily divide our processes among these groups, we can have a multiple queues, not a one queue. Okay, and broadly speaking, we have what is called as a foreground, which are interactive processes, which are more interactive. Okay, which need to be run in a round robin fashion because they are very interactive. And then there are background processes, which are, kind of a batch kind of processes, okay, which you can run in a first come first serve or whatever you say, okay. So that's why we have a multiple level queue scheduling algorithm, which actually, partitions our ready queue into the separate queues, and that will be according to the characteristic of a process, okay. Now, in a multi-level queue, we say we have a foreground and the background, which are the batch kind of things. Each queue has its own scheduling algorithm that we say foreground, because they are very interactive, so they need more quick response time. We know round robin has a quick response time, you can do that. And a background process can run in a batch, no problem. They are not interactive, so let them run a first come first serve basis. Okay. Now between these queues, there can be, excuse me, we can have fixed priority. Okay. What does the fixed priority means? That if we have some a queue in which we have very interactive processes or very of a high priority, and then we have a background processes which are having a low priority. So that means we will run all these high priority jobs, and this queue is empty or not doing anything. Then and only then we can actually run a process from the background, okay, from this queue. Or if a background process is running and some interactive process comes in, we will preempt this. This is the one kind of thing, and this will straight will lead to the starvation. That if these interactive jobs start coming and coming, these jobs will starve forever. So that's the problem. So we can have a different kind of thing, that we have a time slice. We say this is these processes should run for the 80% of time, and this process should run the 20% of time. Okay. And we can run it in such a manner, okay. So like this, this is the Galvin book diagram, okay. Like the highest priority for the system processes, then another queue, the interactive process, interactive editing process, then batch process, and a student process, the lowest one, okay. So we can have these different processes according to different characteristics grouped into different queues with different priorities, okay. Now, this is the basic kind of multi-level queue, which seems to be good, but it's really intensive to make these queues. Why I'm saying that? Because I'm saying this is a batch process. This is not a batch process. Basically, this is non-interactive process. This is interactive process. How do you know that? This is again the same problem with the SJF. Okay. We had, or SRTN, or what do you call it, or SRTF, we call that, do that. If you remember that, we are again telling something, we are queuing processes, but do we know that? Do we know? The question is that. The question is simple as it is. Do we know about a process? So do you know about a process, or you have a priori knowledge about a process? And the simple answer is no. We don't know. So if you can keep a guess, but that guess doesn't work. And if you want to be sure in your things, then you have to make these queues very flexible. This is what we talked about now. And you want to do twofold things. Okay, you want to minimize the turnaround time as well as the response time. Okay, you need to have a quick response time. I mean, process should not wait too much, and turnaround time should also be minimized. So that's overall scenario what we want to do, and that all culminates into what is called as multi-level feedback queue. Now we got a feedback we had an ML queue, multi-level queues. Now we got a feedback. This feedback actually is something which understands the process, okay, and while it's when it understands, not a priori, we don't have an a priori knowledge, but we understand it when it's getting executed. When it's getting executed, on that behavior, we decide what kind of process it is and what kind of scheduling we should do to it, okay.
Okay, now let's work out how actually MLF Queue works. Okay, Basically, we have multiple queues, and they are actually different, having a different priorities from high to low, like we had in the multi-level queue. Okay, so we may have many processes on a particular queue, and they may have different. This queue is having a high priority, then this queue, and then this queue. Now you may argue that if we say this queue has a high priority because we know it is an maybe interactive job, but we are talking that we should not be we don't know anything about the process, and we have to decide. That's what feedback comes in, like I said. So what we do is we just keep a process which comes, we think that it is a short job, interactive job, so we put it in this queue, in the first queue. Okay, and if it runs for a long time, so that means it becomes a long job, so we let it move downwards. Okay, we'll discuss that. So we have some rules in the Mlf queue, right? So the rule number one is if priority A is greater than priority B, so we have two processes, say A and B. Okay, now if A has a more priority than B, then definitely A is gonna run. Okay, and B doesn't, because A has more priority. Now they may have same priority. Okay, if they may have same priority, they will run in a round robin fashion. So give one chunk to the A, then when A gets executed for that chunk, give it to the B. Okay, now you may say again that, hey, if we know the priority, if we know that A has more priority than B beforehand, so it's again a problem, right? But we don't know how we work exactly. I will tell you what exactly Mlf Queue does. Is it sees the observed behavior, and according to that actually it sets the priority. It's not static at all. Okay, so what will happen is when the job comes, we deem it as a high priority job with with, say, maybe like an interactive job. So what do you think is, say for example we give some time slice to it, say t unit of time. Okay, and if B finishes within this time slice, that means it is an interactive job. Because it relinquishes the CPU. That means this is how the interactive jobs work. But if it is running and its time slice is over, that means we say, hey, this is not an short job, right? It is in fact a long job. So what to do is we will make this job to go down queue. Okay, and if, say for example, it finishes into this job, or it leaves CPU, because interactive jobs leave CPU quite often, right? So if A is leaving its CPU before its time slice is over, we will keep it in this queue. Okay, so that means its priority is not reduced, because this is how the interactive jobs work. So let it be there because it's an interactive, because it releases the CPU before the time slice. That means it's an interactive job, so we should not actually decrease its priority. Okay, so by this rule, in this queue only the interactive jobs or short jobs, or those jobs which are not CPU intensive, stay. So they should be having a higher priority, and they should be having more quick response time. So that's why we keep them in this very queue. So our rules will be like this: that if when a job enters the system, it's placed at the highest priority, that's topmost queue. And if a job uses up the entire time slice while running, its priority is reduced, so that's moves down one queue. If a job gives up the CPU before the time slice is up, it stays at the same priority level. That means we think that it is not a CPU bound job, it is rather a interactive job, so it should be in a high priority upper queue. Okay, now let's take a little example that we are saying that, hey, we have a one queue, and say for example only single job comes in, that is the A, and it runs some time slice and it's still going on, so we move it to the B. We move to the next queue, sorry, not B, move to the down queue, which has a lesser priority than this particular queue. Now A is running here, not here, right? So A is not here, A is here. Okay, and since we don't have any job, so it will run in this queue only. Okay, and it again times out to its time slice. It runs for the whole time slice, and it's actually still there. So we say, hey, its priority goes down, so it is gonna work in this, and it starts going on here. Okay, running in this queue. So because it's the only queue, we will still give it CPU, but we are loading it. Okay, because we have now understood, because the feedback, we have understood that this is the long job, so it should not be in this queue, because it's for the short jobs and for the interactive jobs. This is the difference from the multi-level queue and multi-level feedback queue, because in multi-level queue we are saying that hey, short jobs are here, but the question was how we know that. Okay, but here, because the feedback, because it's running still, so we understood it's a long job, it should be in this queue, right? Now for example, some short job comes in, say B, because when the B comes in, we're gonna put it in this queue, because we consider it, because when the job comes in first, we say, hey, this is our this is the short job, so we keep it here. If it runs the whole time slice and still want to run, we'll keep it down. But say for example, this was really a short job and it releases the CPU before the time t, so it will release the CPU. Okay, we will keep it there. If it still wants more CPU, we can keep it there, but if it finishes, okay, but if it doesn't finish, let it be there, because it leaves the CPU, and when it leaves the CPU, we'll start executing the A again, and if it doesn't, we give back to the okay, or if it is finished, we still have to run the A, because we have only two processes here, right? But when B comes back, we will try to give it the CPU again. Okay, this is the scenario right now. So what we are technically saying is, if B is releasing the CPU, keep it there, because of the rule for A, if you could see on the top. Sorry, no, I'm not saying this one. If a job gives up the CPU before time slice is up, it stays at the same priority level, because we don't want to penalize it. Why we don't want to penalize it? Because we think this is the interactive job, which has to do some I/O, and it releases the CPU, okay, quickly. So they need more response time. They have to be in this queue only. Okay, even though we see this has a drawback, this has a bug in it, so we will try to debug that, okay, later on. So right now our situation is like this. Okay, now you can simply see this flaw. Let us try to take the flaws. Flaw number one, say for example, I say that if the new job comes in, you have to, because this job is the long running job, okay, CPU intensive, they don't need the because they're not interactive, okay, and they are running a low priority, and we keep it in a down. And if B comes in, we're gonna give the CPU to the B. If it releases within the time slice, then I'm gonna give it to the A. Say for example, another process comes in, C, which is again kind of same process, which is like a B, which releases the CPU, and some other process D comes in, and E comes in, and so many processes comes in. So if the interactive job starts coming in, what will happen to the A? Differently, it is gonna starve. Okay, so we don't want a starvation here. Okay, we don't want, if this kind of scenario happens, A should still get a chance to run. No starvation should happen, right or not? So what are you gonna do for that? Before we fix this scenario, we can have another situation here. Say for example, some tricky programmer comes in, because we know this rule. So the programmer knows the rule number B of the OS, that hey, if you are releasing the CPU before your time slice, you're gonna stay in this queue. So you stay on a high priority. Say for example, what I do is, I know the time slice, and I say, hey B, for example, I write the process B, and I write it in such a way that when its time slice is say 100%, when it is 99% of a time slice, release the CPU. Just do some fake I/O. Okay, just do some fake I/O. You don't have to do any I/O. Just do it for the sake of this rule. What will happen? What will OS behave? what will this scheduler behave? The scheduler will think that this is a interactive short job, so it should be kept in there. It will not be put into the down queue, right? But actually it is not. It's a long job, but it's me as a programmer has done it. Okay, so this scenario is called the game the scheduler. So what a programmer is trying to do is game the scheduler. So we are trying to do the trick and freaky situation. Okay, so we are trying to sneak beneath this rule 4b, okay, and trying to fool our schedule, right? Because you are relinquishing the CPU at the 99% of time. CPU will keep you the schedule will keep you in this queue. Then later on you will get again the CPU. So you are getting more processor than you should get, right? So we have a couple of problems now. We have a starvation problem, we have the game the scheduler problem. Okay, we don't want to trick someone to trick our scheduler, and we don't want these processes, the long CPU intensive jobs, to starve. So how we gotta fix that? And there may be one more thing. Say for example, some processes are say this is a process going on, and one second. Okay, say for example this is a process going on A, and this much of time was CPU intensive, and then later part is, say for example, IO intensive, and so I'm saying the same process may behave in a first half, it may be a CPU intensive, and then it may be not CPU intensive at all, it may be interactive. Now if we see this scenario, it is gonna stay in the down queue, and it will even not get the CPU at all if the other short jobs start coming in. And even though this is the short job, okay, so this, we have a scenario, we have this serious flaw here in this rule. So we have to actually change our rules a bit. So what we do is we say, hey, like we did last time also, the aging. So if you are aging too much, you are in a down queue too much, what we do is we boost your priority. So we're gonna boost priority, so you get a boost. Okay, so if you have stayed here for long, your waiting time is too long, that's the aging factor comes up, we boost your priority and we let you go up. So likewise, you are down, we get you back to this queue. Okay, then if you have aged too much, we can get you to the top queue even, so A can come back here and can compete with other short jobs for the time slice. And again the same situation happen. If it is too long, again it will run more than its time slice, then we will let it go down, and if it again goes more, it will go down again. So but it is guaranteed that there will be no starvation, right? And again, if it behaves when it, because we said that the scenario like this, that the other half of this process is interactive, so when it comes here and it releases the CPU before its time slice is over, so it behaves now like a interactive job, then we gonna put it there only, we will not move it down. Okay, so this will also help. Now question will be, we say that time S is the time after which it gets some boost. So if it's this much of time, S time, then we'll get a boost to the A, so it moves up. Okay, and this time S is actually it was a John Osterhout. Okay, it was a he's a system researcher. He called this S as a voodoo constant. Voodoo constant. Okay, you should keep it in mind. So this is actually a question, that what should this S be? This is a big question for a scheduler to fix this S, because if it fixes it quite frequently, say for example, I mean if it keeps it very short, then these long jobs will come up above, and it will snatch the CPU time for the interactive jobs. It will defeat the whole priority system, right? And if it is too low, okay, then they will get a lesser, then it will lead to the starvation. So what optimal S is going to be a big question for the schedule. Now we have actually fixed the starvation problem, okay, as well as this problem where the process behaves first be as a CPU intensive then IO intensive. This process is solved by boosting the priority. Now what about the fixing the schedule problem? Okay, for that what we do is we go for the better accounting. What does that mean is we say that, hey, you are a short job, okay, no problem. You have actually we say that, hey, B is a short job, IO intensive job or interactive job because it has relinquishing the CPU before its time slice. We say, okay, you are releasing the CPU before time slice, but if you have run once, we will reduce your priority by 1 and you're gonna stay here. Okay, you are not gonna stay in this queue. So we keep here only those guys which will run only once, say for example. So they are gonna run for second time, they're gonna run in this queue. Okay, so this will improve this will fix this game the schedule problem, because if some guy is coming, say B, it is IO intensive, it is actually faking us and leaving the T, but it is a long job actually. So what will happen by this rule, when I say that, hey, if you run once, you got to go down one priority level. That means now B will start running again here, but it's because it's a long job, it will maybe it will time out here or whatever it will do, because it is run for second time. When it go for third time, it has to go here. So eventually we will see this guy which is faking us stay in the bottom queue like the A, even though A has not faked. A is a real big job and B was not B was a faking, but was a long job. It will still be in this queue at the end. Okay, so this rule will really help. So we're gonna have a rule 4. Once a job uses up its time allotment at a given level, regardless of how many times it has given up the CPU, its priority is reduced. That moves down one queue. Okay, so our both problems, starvation as well as gaming scheduler, is solved. So this is our left side without the rule number 4, and this one is where we have a gaming tolerance. Okay, what will happen if we don't have gaming tolerance is this guy times out. This is the process, the gray, first gray. This will time out before its time slice is over, and we will keep it there. It will start running, we'll keep it there, it times out, then comes back and starts stay in that queue only. But here if it runs once, we'll get it down one queue. Okay, if it again so we'll put it down. That means it will be in a queue with the long job. Okay, then the long job runs, the black one is a long job, and the gray one is the the process which is trying to game the scheduler. Okay, and now this one these two run in a round robin fashion. Okay, so this is the place where it should be, and it will be by the addition of the rule 4. Okay, so one more tweak is done here, that we have now a good scenario. We have now a good algorithm for all these the flaws are removed and everything. And we do one more thing, that we say that the top queue has a shorter burst length than the middle one, and then the smaller last one, it has, say, more than 20 milliseconds of quantum time slice. This because in this queue will be which jobs will be there. Okay, it will be high priority queue, will have the interactive jobs, and interactive jobs need more response time, right? And that's why they have this is how they behave. So there will be some lesser quantum. And then to the bottom, if we say 20-30 milliseconds here, for example, as an example I'm saying, because they are long jobs and that's suited for them, long bursts is suited for them, right? So that's why we have long bursts, so varied number of it's not the same quantum of time we give to the different queues. Okay, now this is really a serious question and not a simple question to answer, that what time slices should we have, What will be the S? That is the time when we start boosting our priority so that they go up the queue, and many more things. So this is a really a complex situation, complex scenario to deal with. So this is our final list of rules for multi-level feedback queue. If priority is A is greater than B, A runs. If they are equal, they run a round robin. Okay. When a job enters the system, we think that this is the high priority job, so we keep it in the topmost queue. Once it gets a CPU time allotment, we will move it down. Okay. So we're gonna reduce its priority, and after some time period S, we give it a boost so that it moves up, so there will be no starvation. So this multi-level feedback queue is interesting, okay, for the following reasons. What has happened to this? Let me. Important thing is we are not demanding a priori knowledge. So we don't have a priori knowledge of the nature of the job. It observes the execution of job and prioritizes accordingly, okay, because we got a feedback and we can do much better. So we are achieving the best of both worlds, okay. It delivers excellent overall performance, like we have SJF and STCF for short running interactive jobs, lesser turnaround time, and is fair and makes progress for long running CPU intensive workloads as well. Okay, we got a lesser here. In the SGF and STCF, actually we increased our minimize the response time. We want to have a lesser response time, quick response time, I can say. Okay, and for CPU intensive jobs as well, we don't have a bigger turnaround time but lesser turnaround times. So that's why there are many systems like BSD Unix and its derivatives like LM plus 89 or B86. We've got a Solaris M06 and Windows NT and subsequent Windows operating systems. They use Mlf Queue, but a little use a form, we can say Mlf Queue, because they have their own tweaks and additions to Mlf Queue, basic Mlf Queue. So whatever we have read is the basic Mlf Queue, and then many systems today, modern systems, use the versions of, I can say, the multi-level feedback queue. Okay, so with this I think this is the end of this segment. Okay, so hopefully you understood this. So until next time, ma salama.